Welcome to this video on degree of static indeterminacy. This is one of several videos in a short course on the analysis of indeterminate structures posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. The objective in this video is to learn how to calculate the degree of static indeterminacy of a structure. That number is essentially the number of unknown forces in the structure, including internal forces and reaction forces, minus the number of equilibrium equations that we have at our disposal to determine the unknown forces. The degree of static indeterminacy tells us which methods are suitable for analyzing the structure. If a structure is determinate, so that the degree of static indeterminacy is 0, then we can simply use equilibrium considerations in order to determine the section forces. If the degree of static indeterminacy is 1 or more, then certain methods that we will learn in this short course on analysis of indeterminate structures are suitable, depending on the degree. The next slide outlines a few important characteristics of determinate structures. As a simple illustration, a simply supported beam and a continuous beam over 3 supports are shown at the top. One is determinate, the other is not. Before we get into the techniques to find out if a structure is determinate, note that there's no need to know anything about the material behavior to find the internal forces in a determinate structure. In other words, the stiffness of the structure does not influence the distribution of internal forces. Another characteristic of determinate structures is that they will never experience any additional forces due to support settlements or temperature changes. Consider as an example the simply supported beam at the top. If this member elongates or bends due to temperature change, then it will not have any additional axial force or bending moment. That is because the support conditions accommodate that kind of deformation. Also, if one or both of the supports settle due to soft soil conditions, then the roller support will accommodate that deformation without imposing any additional forces in the beam. In contrast, the statically indeterminate beam on the right-hand side will definitely experience a bending moment if, for instance, the middle support settles downwards. Such a settlement will pull the beam into a bent shape that certainly causes bending moment. Conversely, if temperature change is causing the beam to bend, the support conditions will prevent it from bending freely. As a result, that situation will also cause internal forces. This is a key difference between determinate and indeterminate structures. Finally, notice that determinate structures do not possess redundancy. The structure will collapse if one member or one support fails. Remove any of the 2 supports of the simply supported beam above, and it will fall down. But remove any one of the 3 supports of the indeterminate beam, and the beam will still be supported. This is called load redistribution, which is a key characteristic of indeterminate structures. The next slide shows the equation we use in terje's toolbox for the calculation of the degree of static indeterminacy. The first parenthesis counts the number of unknown forces. The second parenthesis counts the number of equilibrium equations that are available and adds hinges, which serve to release forces so that they are no longer unknown. Notice that F is the number of internal forces in each member. M is the number of members. S is the number of support reactions, often several per support. E is the number of equilibrium equations per joint. J is the number of joints, and H is the number of moment hinges or other section force releases. Notice also that the loading on the structure does not enter into this formula. That makes sense, because the loading does not influence the degree of static indeterminacy. Rather, that number is entirely a property of the structure itself. On the next slide we see that the number of forces, F, per member depends on the member type. For a 2-dimensional or 3-dimensional truss structure, there is just a single unknown, which is the axial force in the member. For a 2-dimensional beam or frame structure, each member has 3 unknown forces, namely bending moment, shear force, and axial force. Each member in a 3-dimensional beam or frame structure has 6 unknown forces. They are 2 bending moments, one about each of the 2 axes of the cross-section, 2 shear forces, one along each of the 2 axes of the cross-section, 1 axial force, and 1 torsional moment, which we call torque. Now let us look at the symbol E, which is the number of equilibrium equations per joint. For a two-dimensional truss structure, there are two equilibrium equations per joint, namely equilibrium in the horizontal direction and equilibrium in the vertical direction. The same number of a three-dimensional truss structure is 3, because there are now 3 directions along which we can consider equilibrium. For a two-dimensional beam or frame structure, we can set up 3 equilibrium equations per joint. Those are moment equilibrium, equilibrium in the horizontal direction, and equilibrium in the vertical direction. Finally, for a three-dimensional beam or frame structure, we have 6 equilibrium equations per joint. Those are 3 equilibrium equations in the 3-axis directions and 3 moment equilibrium equations, one about each of the 3-axis directions. The symbols F and E on this slide multiply with M and J, respectively. To learn how to count those numbers, namely the number of members and number of joints, it might be best to look at examples. But for now, it can be said that every member will be attached to one joint at both ends. On the next slide, we address the number S, which is the number of support reactions. That number will depend on the support type. At a fixed support, there are 3 unknown reaction forces: bending moment, vertical force, and horizontal force. Similarly, a pinned support has 2 unknown reaction forces. A roller support has 1 unknown reaction force. The more unusual slider support has 2 unknown reaction forces, 1 bending moment and 1 perpendicular to the roller. The last letter we need to address is H. The next slide shows an example on the left-hand side with a small circle to identify a hinge. That symbol means exactly what a well-greased hinge in a door does. It prevents the development of any bending moment at that location. As a result, we know the value of the bending moment at this location in the structure. That bending moment value is 0. As a result, we would set H equal to 1. The example structures on the right-hand side will show that H can be a bit more complicated. Specifically, look at the joint where the upper beam is resting on the lower beam. This is a 3-dimensional structure, so there are 6 unknown internal forces in each member. At this joint, we must ask which of those 6 forces transfer from the upper beam to the lower beam. Perhaps there is no nails or screws or any proper connection at this point, so that it is only the shear force in the upper beam that transfers into the lower beam. That means that bending moments, etc., are released at this location. In other words, this would be a situation where H is 5, because only one of the 6 internal forces transfers from one member to another. The structure below is actually a 2-dimensional equivalent of the 3-dimensional structure above. Here are 3 unknown internal forces per member, and we must ask which one of them transfer at the location of this hinge symbol. If the upper beam is free to roll along that hinge symbol, then the axial force does not transfer from the upper beam to the lower beam. Similarly, the hinge symbol seems to suggest that the bending moment does also not transfer from the upper beam to the lower beam. Only the shear force transfers. As a result, we have 2 releases at this location, so H is 2. The next slide addresses mixed structures. This means that some of the members are frame members, while others are truss members. The author of these notes prefers to count truss members as truss members, but another option is available. First, consider the case on the left-hand side. Here are 2 beam members, each with 3 unknown forces. Here is 1 truss member, having 1 unknown force. There are 4 unknown reaction forces, 2 at each support. Here are 3 joints where a beam member enters. Each of those have 3 equilibrium equations. Here is 1 joint where only a truss member enter. That joint has 2 equilibrium equations. There are no hinges or other releases here, so the degree of static indeterminacy is 0. Notice that if we neglect the cantilevered beam altogether, reducing M and J by 1, the result would be exactly the same. For that reason, it is preferred to simply neglect cantilevered beams in these calculations. An alternative approach is shown on the right-hand side. We now count all members as frame members. That means we have 3 members, each with 3 internal forces. There are still 4 unknown support reactions. We have a total of 4 joints, each with 3 equilibrium equations. But now we need to account for the fact that we have counted the truss member as a regular frame member. We do that by releasing the transfer of moment from the inclined member into the beam. The pin support at the bottom already ensures that the bending moment is 0 at that end of the truss member. So, by setting h equal to 1, we ensure that no bending moment will develop in the truss member, which is indeed the definition of a truss member. Notice that we obtain the same result, which is important. For any given structure, there is only one correct answer. This structure is indeed statically determinate. Now to the next slide. When we are talking about the degree of static indeterminacy, we want to carefully distinguish that from the degree of kinematic indeterminacy, also called the number of degrees of freedom. We get to the concept of degrees of freedom when we learn displacement methods in structural analysis, such as the stiffness method. The frame shown on this slide has a degree of static indeterminacy equal to 3, as shown here. The degree of kinematic indeterminacy is something completely different. Later we will see that computers automatically assign 3 degrees of freedom to each joint of a frame structure. For that reason, we here have a degree of kinematic indeterminacy equal to 6. In hand calculations, we often neglect the axial deformations of frame members. In that case, we have these 3 degrees of freedom, and the degree of kinematic indeterminacy is 3. In contrast, for the degree of static indeterminacy, which is the topic in this video, there is just one single right answer for a given structure. Before we get to the examples, we briefly review another technique for calculating the degree of static indeterminacy. Additional methods are covered in the relevant note at terje.civil.ubc.ca. Toolbox. This slide shows a structure with one truss member carrying a continuous beam. One way to count the degree of static indeterminacy is to cut supports and members until the structure becomes unstable. The maximum number of cuts you make while the structure is still stable is the degree of static indeterminacy. This is an error-prone approach that takes some experience, but let us consider this structure. First, let us cut the capacity of the left-hand side support to carry moment. As a result, that is now a pinned support. Next, let us cut the vertical truss member. Next, let us cut the capacity of the rightmost support to carry bending moment and axial force. We have now made 4 cuts. Finally, let us remove the middle support, namely the capacity of that support to carry a vertical force. The result is shown at the bottom of this slide. Any additional cuts will make this structure unstable. As a result, the 5 cuts that were possible tells us that the degree of static indeterminacy for this structure is 5. Notice on the right-hand side that the calculation method recommended in this video leads to the same result. Now that the concept of stability of structures has been mentioned, the next slide simply makes the following 2 points. If the degree of static indeterminacy comes out less than 0, then the structure is unstable. Take that as a sign of a structure that will collapse if attempted built. Second, a degree of static indeterminacy of 0 or greater does not guarantee stability. One simple example is shown at the bottom of this slide, in 2 different configurations. The configuration at the bottom is unstable, but the degree of static indeterminacy is still 0. The next slide explains another concept related to degree of static indeterminacy. We can distinguish between internal degree of static indeterminacy and external degree of static indeterminacy. To understand this concept, consider this 2-story frame. The total degree of static indeterminacy is 6. 3 of them are internal, 3 of them are external. That is because we count as external degrees of static indeterminacy those unknown reaction forces that we cannot determine with the 3 global equilibrium equations. Moment equilibrium, equilibrium in the horizontal direction, and equilibrium in the vertical direction can only determine 3 reaction forces. In this case, there is a surplus of 3 unknown reaction forces. Is there a way of verifying that the remaining 3 degrees of static indeterminacy are internal? Yes, consider cutting this horizontal beam. By making that cut, we ensure that the 3 forces bending moment, shear force, and axial force at that location are known and equal to 0 at that point. If the supports had been such that the external degree of static indeterminacy was 0, namely with a pin and a roller, we would now have a statically determinate frame. This shows that 3 of the 6 degrees of static indeterminacy are internal for this frame, and 3 are external. Now to the examples. Here is the simplest case possible. It is actually preferred to neglect cantilevered beams altogether when we calculate the degree of static indeterminacy for a structure. That is because cantilevers never contribute to the degree of static indeterminacy. Nevertheless, as a demonstration, we here count 3 unknown forces in the one member. There are 3 unknown reaction forces on the left-hand side. There are 3 equilibrium equations at each of the 2 joints. This structure is statically determinate. Notice that if we arbitrarily selected to make our lives a little harder by including a joint at the middle of this beam, that would increase the number of joints to 3 and increase the number of members to 2. The final result would be exactly the same. When it comes to degree of static indeterminacy for a given structure, there is only one correct answer. The next slide shows an example that is nearly as simple as the previous one. Here are 3 unknown forces in the one member. There are 2 unknown reactions on the left-hand side and 1 unknown reaction on the right-hand side. There are 3 equilibrium equations for each of the 2 joints. The result is that the simply supported beam is statically determinate. The next slide shows a continuous beam with a cantilever. We start by removing that cantilevered portion of the structure from our considerations. Cantilevers are statically determinate entities that we can find the internal forces in solely by equilibrium. In this case, we have 3 unknown forces in the 2 remaining members. We have 3 unknown support reactions on the left-hand side, and 1 reaction force in each of the other 2 supports, for a total of 5 unknown reaction forces. We also have 3 equilibrium equations for each of the 3 joints. The result shows that this structure is indeterminate to the 2nd degree. Here is a beam with an ordinary hinge at the middle. We count 3 unknown forces in each of the 2 members. There are 3 unknown reaction forces on the left-hand side, and 1 unknown reaction force on the right-hand side. There are 3 equilibrium equations for each of the 3 joints. And then we count 1 hinge for the hinge symbol shown here. The result is that this structure is statically determinate. The next slide shows a truss example. There is 1 unknown force, namely the axial force, in each of the 16 members. With 1 pin support and 1 roller support, there is a total of 3 reaction forces. For a 2-dimensional truss structure, there are 2 equilibrium equations for each of the 8 joints. The result is that this structure is in the indeterminate to the 3rd degree. You would get the same result if you decided to connect the truss members where they cross each other. In that case, you would count 22 members and 11 joints, again leading to a degree of static indeterminacy equal to 3. The next slide shows a similar truss example. This type of truss is more common in houses built with wood frame construction. There is 1 axial force unknown for each of the 11 members. As with the previous structure, there are 3 reaction forces. There are 2 equilibrium equations for each of the 7 joints. The result is that this roof truss is statically determinate. Next, we consider a 3-dimensional structure. The figure shows 3 beams resting on a lower beam. Before we can calculate the degree of static indeterminacy, we must clarify certain details on how the supports and connections are constructed. First, we prescribe that there is only 1 force transferring between each upper beam and the lower beam. The upper beams are simply resting on the lower beam without any form of nail, screw, or other connection device. Second, we make a similar assumption about the rightmost support, where the lower beam rests on the ground. We assume that only 1 force transfers from the lower beam to the ground, without any restraint on any displacement and rotation other than the vertical direction. Although this is a 3-dimensional structure, we can actually analyze it as a 2-dimensional structure. However, let us first calculate the degree of static indeterminacy as a 3-dimensional structure. In that case, there are 6 unknown forces for each of the 8 members. Notice that we count the members between all joints separately. There are 6 reaction forces in each of the 5 fixed supports, and there is 1 reaction force at the end of the lower beam. That means there are 31 reaction forces at the supports. We have 6 equilibrium equations available at each of the 9 joints. Finally, we must determine the value of H. As mentioned earlier, we assume that only one force transfers from each of the upper beams to the lower beam. That means the other 5 internal forces in each of the upper beams are released at these connections. There are 4 connections, which implies that the total number of releases, namely the value of H, is 20. The result is that the structure is statically indeterminate to the 5th degree. Now let us consider all these beams as being two-dimensional. In that case, there are 3 unknown internal forces in each of the 8 beams. There are 3 unknown reaction forces at each of the 5 supports, plus the single reaction force at the end of the lower beam. That means S is 16. We have 3 equilibrium equations available at each of the 9 joints. Only one force transfers where each of the upper beams rests upon the lower beam. That means the other 2 internal forces in each of the upper beams are released at these connections. 4 connections with 2 releases in each means that H is 8. We observe that the degree of static indeterminacy is 5, which is the same result as when we considered the structure to be 3-dimensional. That is exactly what we should expect, because it is the same structure we are addressing, and there is only one correct degree of static indeterminacy for a structure with given support conditions and connection details. The next slide expands upon the assumptions that are needed at supports and connections. By looking at this figure, it is not immediately clear what kind of support conditions are present. As a matter of fact, certain assumptions will make the structure unstable, so this structure requires careful attention. The following choices are made and conveyed to the contractor who carries out the construction according to these specifications. First, we prescribe that only one force transfers between the 2 beams at point B. This means that both beams are free to displace and rotate independently in all other directions at this location. Second, we say that only one force transfers into the ground at point C. This means that all other displacements and rotations can freely occur at this location. Third, we say that only one force transfers into the ground at the middle support of the upper beam at point D. This means that all other displacements and rotations can freely occur at this location as well. Fourth, we prescribe that no displacement can occur at point A and point E. If you attempt to calculate the degree of static indeterminacy at this time, you would get a negative number. That means the structure is still unstable, even with the assumptions that we have made so far. For example, none of the beams are prevented from rotating about their axis. For that reason, the 5th prescription is to prevent the beams from rotating about their own axis at point A and point E. The structure is still unstable. That is because the upper beam can freely rotate about the vertical axis at point E in a manner that makes it slide back and forth on the lower beam. Similarly, the lower beam can freely rotate about the vertical axis at point A so that it slides sideways at point C. To prevent those motions, we could introduce a better connection between the 2 beams at point B and a better connection to the ground at point C. However, there are different ways of doing this. For example, an equivalent approach, in terms of making the structure stable, is to prevent rotation about the weak axis of each beam, namely about the vertical axis, at point A and point E. As a result of all these assumptions, we have a total of 12 support reactions. That includes 5 at point A, 5 at point E, 1 at point D, and 1 at point C. We also have released 5 of the 6 internal forces in the beams at point B. The formula then looks like this. There are 6 unknown forces in each of the 4 members. Notice again that 4 members are counted, although, practically, there are only 2 beams. That is because we always must count the members that go between the joints separately. There are 12 support reactions. There are 6 equilibrium equations for each of the 5 joints, and there are 5 releases. In short, this structure is statically indeterminate to the 1st degree. That makes sense, because if we release the one single force that is currently transferring from the top beam to the bottom beam, then these would be 2 separate and statically determinate beams. The next slide wraps up the point that the 3-dimensional structures we have addressed on the previous slides can be considered as 2-dimensional structures. The structure shown here is 2-dimensional from the start, and we count 3 internal forces for each of the 4 members. There is a total of 7 reaction forces. There are 3 equilibrium equations at each of the 5 joints. We let the upper beam freely slide and rotate on the lower beam at point A, as suggested by the hinge symbol, which can here be interpreted as a rolling ball. That means that we release the axial force and bending moment at point A. That means H is equal to 2. We conclude that this structure is statically indeterminate to the second degree. Next, we address a straightforward 3-dimensional frame. There are 6 unknown internal forces in each of the 13 members. There are 6 unknown reaction forces at each of the 6 supports. We have 6 equilibrium equations available at each of the 12 joints. In the end, we find that the degree of static indeterminacy is 42. Because we can establish 6 global equilibrium equations for a 3-dimensional structure, 36 of the degrees of static indeterminacy are internal. To distinguish external from internal degrees of static indeterminacy is not particularly important in structural analysis. In the next example, we return to the point that it is possible to count truss members as frame members, and then introduce releases to make sure the truss members act like truss members. The final result will be the same. This slide addresses first the recommended approach, which is to count truss members as truss members. That means there are 3 internal forces in each of the 2 beams. There is 1 internal force in the truss member. There is a total of 5 reaction forces at the supports. We have 3 equilibrium equations at each of the 3 joints where the beam member enters. We have 2 equilibrium equations in the joint at the top, where only 1 truss member enters. In this case, we have 0 releases. The result is that the structure is statically indeterminate to the first degree. Now let us count the truss member as a frame member. That means we have 3 unknown internal forces in all of the 3 members. We still have 5 reaction forces at the supports. We have 3 equilibrium equations available in all of the 4 joints. However, we must now introduce a release at the bottom of the truss member. We place a hinge there, so that H is equal to 1. Otherwise, bending moment could transfer from the beam into the truss member, and that would be a different behavior than what is intended with this structure. The final result is the same. This structure is statically indeterminate to the first degree. If it was difficult to understand the point of introducing releases in truss members, then this next example may help. First, we do the recommended approach, counting truss members as truss members, which does not involve the difficulty associated with artificial releases. Here we simply count 4 beam members and 5 truss members, without introducing any releases. Notice that we only have 2 equilibrium equations at the bottom joint, where only truss members enter. The result is a degree of static indeterminacy equal to 3. This makes sense, because if we cut 3 of the truss members, then the remaining structure is statically determinate. Next, we count the truss members as frame members. That means we have 3 unknown forces in all the 9 members and 3 equilibrium equations in all 6 joints. Carefully notice that we now have 9 releases. We place a hinge at the top of every truss member to prevent them from getting any bending moment transferred from the beam. Importantly, we only need 4 releases at the bottom joint. The reason is as follows. When you have placed a hinge at the bottom of 4 of the 5 truss members, then there is no way that they can transfer moment into the last member, which does not have a hinge. For that reason, it would be a mistake to introduce a hinge at the bottom of all 5 truss members. Again, the result is a degree of static indeterminacy equal to 3. The next example lets the dust settle on the paradoxical introduction of hinges in truss members. Here we simply use the recommended approach. There are 3 unknown forces in the single beam member. There is 1 unknown force in each of the 3 truss members. There is a total of 4 reaction forces. There are 3 equilibrium equations in the 2 joints where the beam enters. There are 2 equilibrium equations at the 2 joints where only truss members enter. With this simple approach, there are no releases to ponder, so H is 0. This structure is statically determinate. Finally, we address 3 portal frames with different supports and connections. The leftmost frame has 3 unknown reaction forces and no hinges, so this is actually a statically determinate portal frame. Notice the roller support on the bottom right. The middle frame has 2 pin supports and 1 hinge where the bending moment is released. As a result, this frame is also statically determinate. The rightmost frame is completely fixed at the bottom of both columns. However, there is a hinge constructed at each of the 2 connections between the columns and the beam. Counting 1 release at each of those 2 locations means that H is equal to 2. As a result, this frame is indeterminate to the first degree. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.